is I want to list the vial group elements across the top. And I like to do this starting from longest to shortest. So this is the longest. Here's the identity element. And then maybe there's some simple reflections over here. And then there's sort of random elements in the middle. And then down the left side, I want to list integers. What goes in, so if this is the integer I, so what goes in row I and column W is exactly this integer. So it's the rank of the constant sheaf HI of F restricted to XW circle. Okay. And this kind of thing, I'm going to refer to this as, so you get it, if you fill out this whole table, you get a table of integers. And I'm going to call this the table of stocks. Okay, so.
Excuse me. How
yes.
do you get negative integers as ranks?
You don't get negative integers as ranks, but the integers here are the degree in which you're taking cohomology. So the chain complex can have terms in negative degrees. So,
okay,
so,
yeah, okay.
It does, yeah. So, this is one sort of foundational fact about sheaves is that the functor of restricting to a subset is exact, and so that's why it commutes with taking cohomology. Okay. All right. So here's one more ingredient about this derived category of sheaves. There's an operation called Verdier duality, and the notation for it is this boldface D. So it's a contravariant functor from this derived category of sheaves to itself. So because it's contravariant, I'm going to put a little op here. So what this functor does is it's basically a really fancy souped up version of taking the dual of a vector space. So in particular, one key property is that if you do Verdier duality twice, that's the identity functor. If you do it to, if your topological space was just a single point, then Verdier duality is really just taking the dual vector space. So yeah, so this is a fancy version of vector space duality. Okay, so I'm going to need this mainly to play some role in a definition. So here's part two of the talk. So parity sheaves were one of the ingredients in the title of the whole mini course. So here's a definition. So an object F in this derived category is called even if, well, basically, if the table of stocks has entries only in even numbered rows. That's equivalent to saying that when you take these cohomology sheaves, you always get 0 if I is odd. So the table of stocks has non-zero entries only in even numbered rows. Okay, so that's the definition of an even object. And now, of course, you can guess what it means for an object to be odd. You just swap the roles of even and odd. So f is odd if, well, it's the same idea. And then f is parity, basically if it's one or the other. Probably some people in this room will complain that this is not general enough. And that with this definition, parity sheaves don't form an additive category. So that's true, but I think it's basically going to be clearer for my talk if I define parity to be this. So.
You mean this to be star even?
What's it? Oh, sorry. You're right. Okay, I left out a condition, which is the point of introducing this. Yeah, thanks. Yeah, what I meant to do is put this condition on both f and its Verde dual. So let me just insert that in here. So hi of f equals 0 and hi of the Verde dual of f equals 0 if I is odd. Yeah, so Verde duality, I mean, I want to give you mixed messages about it. On the one hand, it's a generalization of vector space duality, which is a really familiar thing. And on the other hand, it's this subtle thing that where if you write down the table of stalks of some constructible complex, you can't in general read off what its Verde dual looks like from that. That's extra information that I mean, you know, that's just a version of saying that this table of stalks, it's important information, but it's not enough to reconstruct this chain complex. So. Okay. Let's see. So now I want to do something that is more that has a bit of a theoretic feel. So far it's been about sheaves in a pretty general setting. Like I had G mod B, but that, you know, a lot of what I said so far you can say for very general topological spaces. So now I want to let S be a simple reflection. And then let PS be the corresponding minimal parabolic. So I think maybe Alan called this P alpha. Is that so the picture you should have in mind is that you take the Borel and then you allow a non-zero entry in one extra spot below the diagonal corresponding whichever simple reflection you picked. And then, so of course, this PS, it contains the Borel you start with. And so there's a map from G mod B to G mod PS. I mean, you're modding out by the Borel, now you're modding out by a bigger group. So of course, there's an obvious such quotient map. And I want to call that map pi sub s. Now they're functors. So far I've been talking about sheaves on G mod B, but of course you can also talk about sheaves on G mod PS. And they're functors going both ways. I mean, these are examples of a very general theory where when you have any continuous map of topological spaces, you can move sheaves back and forth along the continuous map. And so there's something called a push-forward functor here, which is called pi s lower star, and over here there's a functor going back called pi s upper star. And I want to introduce a new notation. I want to define a new functor called theta sub s. And it's going to be a functor from this category to itself, where I push forward to G mod PS and then pull back. So it's pi s upper star composed with pi s lower star from mod B k to itself.
Can I ask, when we go to Gmod P sub s,
Mhm.
can we think of that as removing one vector space from the flag?
Yeah, that's exactly right. Yeah. Yeah. So speaking of that, so let me make the observation that the fibers of the map Gmod D to Gmod PS. They all look like the well, it's the space of choices. I mean, if you're thinking about this concretely, where this is the space of complete flags, and this is the space of flags where you're skipping one step, the fiber over point is the space of choices for that thing you can fill in. And those fibers look like PS mod B, and Alan told us yesterday what the space is, so someone want to volunteer this information? Yeah, it's CP1. Yeah. Okay. So here's a proposition. So part one says that if F is parity, so if F is a parity sheaf. So in other words, I'm taking an object on Gmod B, which satisfies, it should be either even or odd. So that means that when I draw its table of stocks, it's only in even numbered rows, and the same for its Verdi dual, or both of them are only in odd numbered rows. Then when you apply this functor, you still get a parity sheaf. And then part two says that if F is supported on X sub Y, where Y is an element of the Weil group, and if Y is less than Y times S in the Bourgeois order, then theta SF is supported on X sub ys. So supported on means that it's restriction to any B orbit outside of this better be zero. That's what support means. So I think I'll say a little bit about what goes into this.
Is there something to be said if S is in the right descent set of Y? If ys is less than Y?
So if ys is less than y, then the support doesn't change. Yeah. Okay. So the proof idea. So for one, so I said at the beginning that this lecture is about algebraic topology. So one thing that happens when you push forward a constant sheaf is that so push forward of a constant sheaf is closely related to computing the singular cohomology of the fibers of the map. So this is singular cohomology, like you would learn in a beginning course in algebraic topology. So what's relevant for part one is we're going to do a push forward along pi s, and the fibers of that map look like CP1. So the key point is that the singular cohomology of PS mod B with coefficients in K. So this is the singular cohomology of CP1. So what does one know about the singular cohomology of CP1?
Concentrated in degree 0 and 2.
It's concentrated in degrees 0 and 2. And actually, I need less information than that. I just need that it's concentrated in even degrees. So what happens is that if you want to compute the table of stocks for the push forward from the table of stocks you had upstairs, you have to modify it using this cohomology, and those modifications just change things in even degrees. So this is the key point. So I think to get into more details about this calculation, it would take us a bit further afield, but there's a point I like to emphasize when I'm doing this kind of stuff, which is that I think we've all had the experience of teaching calculus, and you come across a student who can take a derivative of anything. They know the power rule and the chain rule and all, but they can't tell you what the definition of a derivative is, and even if they can't tell you how it's connected to the algorithm they're able to carry out. And then that's always like a bit of a disappointment. But actually, it's the experts in these sort of sheaf theoretic methods. The secret that they know is that there's all this background machinery that goes into making the definitions of things like this derived category precise. But at the end of the day, when you want to compute things like this, it comes down to a pretty short list of rules like the chain rule, and this is at the end of the day, this is a pretty easy calculation. So anyway, so I of course I haven't been able to tell you enough background to show you how easy it actually is, but maybe you find that a little bit convincing. And then what goes into part 2 is basically something about combinatorics of the Bruhat decomposition. Part 2 actually, it hardly involves any sheaf theory, it just involves looking at the images and pre-images of various Schubert varieties under pi s. Okay, so now here's a theorem. So this is due to Mautner Williamson. So the theorem says that for every element in the Weil group, there exists a unique parity sheaf EW with the following 3 properties. So one is that it's supported on XW. Number 2 is that if I take EW and I restrict it to the largest orbit in its support, so XW circle, then I get the constant sheaf in degree negative the dimension of that orbit, and 0 otherwise. And this negative the dimension thing, this is, of course, you can make some other choice here. I mean, you can just move the terms of the chain complex to change this. But this turns out to be a very convenient normalization, so it's pretty standard. And then the third property is that it's indecomposable. So it doesn't break up as a direct sum of some smaller objects. So I think the proposition I stated over there implies the existence of this. The main new maybe the hardest part of this theorem is the uniqueness. Okay, so the main question I want to ask here is what is it? And the answer to this kind of question in this kind of sheaf theory context the answer should never be of the form of an explicit chain complex. That's just too much information, and you don't know what to do with it. The answer I want is this. I want to know what its table of stocks is. So in characteristic 0, there's a very deep theorem that has its origins in deep ideas from number theory, and it's called the decomposition theorem. So if the coefficients are also complex numbers, so far the spaces have been complex varieties, but the coefficients have been whatever. But if k equals c, then you can use the decomposition theorem. And so it implies that the direct summands, that the indecomposable direct summands of anything we do in this way. So basically, I want to look at objects that you get from applying these thetas to a parity sheaf, and maybe I want to start with the most basic parity sheaf, which is the constant sheaf on the zero-dimensional on the one-point Schubert variety. So the decomposition theorem implies that the indecomposable direct summands of these are what are called intersection cohomology complexes. And the notation for this is ICW. I'm going to put C in parentheses to indicate that this is some chain complex of sheaves, but the coefficients for the sheaves are again, the complex numbers. And in this case, Kazhdan-Lustig theory answers this main question. Yeah, so Kazhdan-Lustig theory gives the answer. And I'll tell you what the answer is. So I guess Kazhdan-Lustig polynomials have been mentioned a few times now. So Ivan mentioned several different variations of these in his talk, and I mentioned them yesterday. So let me give you one precise formula. So there are various versions involving affine Weyl groups and parabolic versions and whatever. So Kazhdan-Lustig polynomials for the easiest case is just to look at the finite Weyl group. So what you do is for each pair of elements y and w in capital W, there exists a polynomial pyw of q, and this polynomial has the satisfies the following equation. So the coefficients of the polynomial are basically entries of the table of stocks for one of these intersection cohomology complexes. So the formula is you take minus L of W plus 2I. So this is a sum of I, where I is any positive integer of ICW of C restricted to XY circle times Q to the I. So in Ivan's talk, Q is a number, but here Q is just a variable. And so this is a polynomial, and the coefficients are exactly the entries in the table of stocks.
All the entries are just one row or column? Or?
So if you fix y and w, that gives you a single column for ICW, and as you vary y, that gives you the entire table for ICW.
So is there something that records the entire table both ways?
I mean,
Oh, that does it?
well, if you fix y and w, that gives you one column, and you vary y to get the other
Okay,
columns.
okay.
Yeah.
Okay.
And but by the way, you can see in the formula that ICW is going to be a parity sheaf. The only cohomology sheaves that occur have, they all differ from the length of W by an even number. So it's either all odd numbers or all even numbers. And so Ivan also mentioned that there's a combinatorial algorithm for computing these, and the combinatorics. I mean, you can say it you can say what the algorithm is in a completely combinatorial way, without ever mentioning topological spaces. But if you try to understand the proof of this equation, so this theorem is due to Kazhdan and Lustig from about 1980. They proved this sort of simultaneously with inventing Kazhdan-Lustig polynomials. And if you go through and read the proof of this, it's clear that they had this in mind at the time that they described the combinatorial algorithm. The combinatorial algorithm is basically the algorithm for applying pious lower star and pious upper star to the table of stocks, starting from the easiest thing which you can do, which is this thing that's supported on a single point. So yeah, so the content of this theorem is sort of like it comes down to relatively elementary algebraic topology, like computing the cohomology of the two square. Okay. Okay, so now let me talk about general K. So this problem is solved for K equals C. Maybe I should put parentheses K here to remind you what the coefficients are. So if K is not equal to C, this is something that actually a reasonable amount is known about, but it's too hard for this week. So let's try to solve an easier question. What's that? I don't know. It's like 90 degrees outside, and I don't know who wants to compute intersection forms when it's that hot. So I want to do something easier. So I want to start drawing the tables. For ICW of C and for EW of K. So these are both tables of integers, and this one I have a combinatorial algorithm for. So this one I definitely know the answer to. This one I don't know, but maybe I can answer some questions about it. So when I say start drawing the tables, I want to start at XW naught. So this is the leftmost column where they're non-zero. And I'm going to start at that column and move to the right. So the questions I want to ask are.
You meant for the subscript to be the longest word?
Usually subscript 0 in there. Maybe it should be X upper 0.
No, I mean the W naught column is going to be 0 unless W equals W naught. I really mean start at start at the column labeled by W. I mean you can start at W naught, but you'll just have all zeros until you get to something in the support of the thing. So start at column W, and then move to the right. Where is the first place where they might possibly differ? And do they actually differ? And I think I want to keep this table here. I mean, I'm not really going to use it, but I don't know, maybe it's nice to look at that table. So I want to say something about these easier questions, but I want to switch settings. So I'm going to briefly talk about something that looks like it has nothing to do with flag varieties. So I want to talk about something. I think this is part 3. I want to talk about a very special situation. So the setup is going to be this. So I want to let Y be a conical affine variety inside C to the n. And conical means stable under the scaling action of C star. And, well, an affine variety has to be closed, so it's automatic that it contains the origin in this case. So I want to assume that that Y minus the origin is smooth, and I want it to have even complex dimension. So I want its dimension to be 2D, so 2 times something. And then I also want to assume that there exists a resolution of singularities called I'll call it pi, from Y tilde to Y. And I want this resolution to obey a rather large number of special conditions. So here are the conditions on this. So one is that this should be, so resolution of singularities means in particular that Y tilde is a smooth variety. And I want this to be an isomorphism over the preimage of everything other than the origin. So this is an isomorphism. And then I want to let F be the preimage of the origin. So this is the only point where this map does something strange, and I want to assume that that F is smooth, and that it has dimension half this number, half the dimension of Y. And then the last thing is that I want to assume that Y tilde has the structure of a vector bundle over F. Okay, so if you have all of these conditions.
Is it
Yeah?
possible to give an example?
Yeah, okay. So in fact, all the exercises for today are about examples of this setup. Here's probably the easiest one. The easiest one is this. Oops, this is not. So I want to let Y be the space of nilpotent 2x2 matrices. inside C4. So 2 by 2 matrix, the space of 2 by 2 matrices is basically the same as C4, and so this is an affine variety, and it turns out that if you're nilpotent but you're not the zero matrix, then this is the set of matrices conjugate to a nilpotent matrix with one Jordan block like that. And so because it's a single conjugacy class, it's smooth. The dimension in this case turns out to be 2, so that's an even number.
My dear, let me give a complicated description of this variety. It's a quadratic cone.
Okay. Okay. Right. So, yeah. So, if you take a nilpotent, yeah. So this is nilpotent if and only if A equals minus D and the determinant is 0. Then you can simplify these equations into something like, if you simplify and change coordinates, you really get something like x squared plus y squared equals, wait, what do you get?
Well, it's a squared plus bc equals to 0.
A squared plus bc equals to 0, yeah, okay. Yeah, okay. Okay, yeah, so here's an easy description of this variety. But it's convenient to think of it as nilpotent matrices because for y tilde, I want to take the set of pairs of the form xl in y cross p1 with the condition that so p1 is the space of lines in C2, and the condition I want is that L is contained in the, there's a mistake in the exercise which Mackie pointed out to me this morning. So in the exercise it says L is contained in the kernel of X, and that's the wrong condition. It should be that L contains the image of X. So sorry about that. So you have to do a little bit of work. I don't know what the shortest way to say it here is, but this turns out to be actually just the cotangent bundle of P1. So if you fix L, the space of possible x's is a vector space, and it's one-dimensional, and
So I think it's the first example of love in any algebraic geometry.
the first example of what?
Oh
yeah, it's the first
example.
Is it the first example? There's not.
Second example.
It's the second example, yeah.
I guess you could do n by n matrices as long as you said rank 1.
Yeah, that's precisely the homework problem. Yeah. So everyone listen to Alan. Okay. So here's here's what I want to do with this. So whenever you have a vector bundle,